Okay, everybody. Okay, so as you can imagine, the choice of heuristics is rather important in if you want to win your games in reality, and that will be one of the things that you can play around with in the implementation of your own engine for the first assignment. So how can we come up with a good procedure to estimate whether a state is good or not? And the same discussion we had about the heuristics in single player or single search, we now have with adversary search, apart from the fact that you can have more complex features that you want to involve in the game. So one of the requirements of this evaluation function by heuristics is that it should order the things in the same order as you would with the utility function. So if you win, then you should also be high in the ordering of the heuristics. It should be fast, because if it takes too long to calculate the heuristics, then the algorithm will even be more inefficient. And then actually, for the actual states, the evaluation function, the heuristics should really be the same as the one in which you would win a game. There's not always games, or there's not always situations where this will always work. So if you have a high fluctuation, swings in the values in the near future, then it's very difficult to use those heuristics to guide you through the search process. Let's look at some ideas. So this is a game where we don't have a chess game where there's no information yet. So the game has just started. Why it is going to start? What kind of heuristics would you apply? Wait a second. We have so here we have, for example, the heuristics of the number of figures that you have on your hand, or that have already been played. So you would be counting the numbers. In this situation, you would have 3 of the more powerful, 2 of the more powerful ones. Here you have the queen taken. So basically, you have, for different situations, you have different heuristics that you could apply, and you can then even calculate your true evaluation function as a combination of the different heuristics that you have, given some weighting. And this is basically what we're going to do for the learning part in the assignment, that you can learn those weightings for those features that you have in determining your heuristics. So that was what I talked about yesterday, the learning of the heuristics. That is something that comes back here if you have different weightings. This doesn't always work, and this takes a bit too long now to show it. All these estimations, so there's in history there are beautiful games, and this has even this name, where you have a player really playing against a certain heuristics and giving away many of the figures in the game in order to achieve the chess mate at the end by some other advantages achieved. And in chess, for example, the positioning of your figures, so it is very important, and that was what could be seen in this game, that black gets into a very defensive position, and even though at the end of the game black wins a lot of figures, it will in the end lose the game, with white having hardly any powerful figures left. So here now we see the situation where white loses a pawn. I think here it is losing the castle. But what happens here is that the position itself gets so good that in the end you get a chess mate situation in the next move. And that is, so now even the queen was lost, and now you get the chess mate situation. So having a certain strategy, certain heuristics doesn't always get you to a goal. So this is just one example, but you know it. So that, I think, what makes it fun, and this is also what makes it difficult to devise good heuristics for different game situations. There's one example which is has a name of these problems with heuristics, and that's called the horizon effect. And that is that we have to make a conscious decision when we build those algorithms of saying we cut off as a certain point. So let's look 20 steps ahead, and after that we believe that it will be fine. And that works, in many cases works very well, but this is an example here where it doesn't work, and it's called the horizon effect, that there might be, after many, many moves, and we don't know how far it is, we can't see the step afterwards. And in this case, there is a radical change here. So these are all white figures, and this is black. And so this is a white pawn that can turn into a queen in the next step. And that would decide the game. So then white will win the game. But black has an option of changing this. So at all of these states, black would be better in the heuristics, but white is going to win because at a certain point, black runs out of options. And the point is, we don't know yet. It's quite a long way before that happens. So what black can do basically is say set chess here, and then white can move. So black always has to set chess, otherwise he loses. So if you set chess here, then white can move, and it takes about 10 moves before the white king has moved to a position where you can't set chess anymore. So we know that in 10 moves, white will win, but in these 10 moves, nothing will change in the heuristics for which white is still rather badly positioned. And that's called the horizon effect, that we have no idea how deep our cutoff has to be, and if you do the cutoff in the calculation of the estimation, then you will make the wrong move here. So, as I said, in the next weeks, we are really focusing also on learning these heuristics. How does such a learning algorithm work? What are the principles of this? Because, of course, the big success of AlphaGo in this huge space of Go is, for a large part, due to very clever search techniques, but also very good heuristics that were learned from games as well. Before I go back to the minimax algorithm and show you how to calculate this more efficiently, I want to have a very quick talk about multiplayer games, because everything I had so far is just two values. So either you have min-max and that alterates, or it might follow some other rules, but in principle, you have only two players. But the same principle can also be applied to games with more players. So here you have, for example, a three-player game where we have player A, B, and C alternating in moves. And then the only difference is that the min-max values are not simple values anymore, but they're now vectors of values. And then, according to the rules of the game, you are in a situation where A starts to play, and these are the best positions A can be. And then you would take the A value in this vector, on the basis of which you would then apply the algorithm, the maximizing algorithm for A. So A maximizes the first value, B maximizes the second value, and C maximizes the third value. And then you can apply exactly the same algorithm to calculate the utility value for player A when he or she has to make the decision. So that was just a very quick extension of the method from 2 players to more players. So it's just exactly the same algorithm, but now you need different utility values, and you just store them in vectors. Another extension of the idea is to get into the element of chance. If you have a game where we don't have deterministic moves, but where we do not know at which state we end after a certain phase. And gammon is an example here. The gammon has the rules that you are in have your figures in some starting position. I think it's this one for white, and you can move your stones according to what the result is from the dice, throw the dice. And basically, what you can do in this game is that you can calculate the probability of how likely is it that a certain state comes up, a certain number comes up with two dice. You have possibilities of the moves that the max player can make are then exactly in the same way. The states that you can reach are, I think, that from 5 to 10 and 5 to 11. These are the 19 to 24. So basically, depending on the choice of how the dice fall, you have again different moves that you can legally make in the game, and then you can increase the level of in your search tree where the nodes get assigned a certain value of probability that it could be reached. And if you throw with two dice, you know that 2 has a probability of 1 over 16, so 36 is the max. It's the different possibilities you can throw a dice, so that the outcome is a 2, has a certain probability. And we're going into the details of this probability in next week, but so you can assign a value of this node, this state to happen, and then you can basically extend the notion of the max value that you can reach in this game by a certain probability that this can take. And you can make the decision based on one of those maximizing choice. So take the most probable node, that would give me the highest result. And this is something that you can combine in this search tree as well. So the chance nodes are first-class citizens of this tree as well, as I tried to explain. I want to skip. This is the example I was saying, that throwing a 1 and a 1 has a lower probability than, so a value 2 has a lower probability than any others, which have a 1 over 18 probability. And that might determine your choice of the way you position your figures in this game. And the algorithm is then exactly the same, apart from the fact that you also add a chance node evaluation, where you try to then sum up over the possible probabilities for the certain states. But in principle, the algorithm is exactly the same. So I want to get back and spend more time now on an extension of the minimax algorithm, which is alpha-beta pruning. And we'll see that this is really a very powerful adaptation of the algorithm to really allow you to search far more deep in the tree without losing any information. That is the general idea. So the problem of minimax is that the number of game states that you have to look at is exponential to the number of moves. So that is prohibitively expensive for real applications. And the solution that you want to have is, and that holds to actually even if you have, even if you cut off, so it's not just impossible to calculate all the possible moves in chess up to a certain depth, because we can't go to the end node. So, but because even for a depth of 10 or 6 even, the search space becomes so big that it takes too long to calculate because of this exponential growth in nodes. So the idea is that can we get rid of certain nodes and look at only parts of the tree without losing information? And that's the idea of alpha-beta pruning, where you keep now not a value of a node, of expected values for a node, but where you keep an interval. So you choose now the biggest value and the smallest value that your node can get. And based on this bookkeeping of the lowest and the highest value, we can prune parts of the tree. So we keep track of alpha value, which is the value of best choice found so far at any point along the max path, and we choose the beta value, which is the best choice found so far for any min paths. Yeah, sounds complicated, is not that complicated. Let's look at the example again. So what you do in the algorithm is that you start now with not a value, but the interval, and you give it the two extreme values because you want to calculate the mins and the maxes. So you start with the infinite interval, and then you propagate things down as we did before with these recursive calls. When we end up in a bottom node, in this case the 3, we backpropagate this value already, so we don't calculate all those subtree values, but we backpropagate this value as soon as we have it to the min node up front. And the min node then adapts the beta value of its interval according to this information. What that says is that if min is allowed to choose, then it will always choose something that is 3 or smaller. That's all this says. So even if this is now a 12 or a 15, then min will always choose 3 or smaller. So basically this is a message to max: you will never be able to do better than 3. Yeah? And then in the next step, when I find a 12, I don't need to update it because I already have the min value that max can ever better. And then I do it for the last one as well. Okay. And now I know that this is precisely the value, and I can now do this, give this value back to the max node on top. And what does it mean now? It means that max will always be able to choose something 3 or smaller. 3 or higher. Yeah? So the alpha value becomes now 3, and the beta value, so the highest value that max can achieve, is not yet determined by this example. Okay, let's go on. Then remember, we do depth first search to the end nodes here. Then you go to the first of the leaves. The value is 2, so we adapt the beta value of the interval on the node above. And now what we can check is that this beta value is smaller than the alpha value of the node above. And that basically means that we don't have to look at those nodes anymore. Why is that? What this basically says is, let's look at this tree again. It says that min chooses a 3 here, and that means that max will always find something that is 3 or higher. What this says is that as min has already found a 2, it will always choose something which is 2 or smaller. Yeah? So basically in this node the information comes together that min will choose something that's 2 or smaller, and max will choose something that's 3 or bigger. So all this information becomes irrelevant. Yeah, is that clear? Yeah? And now this looks trivial because we have not looked at these 2 nodes, but suppose that we have now a level of, I don't know how many depth first searches we do, how deep we search in the tree. There could be a very complex, huge search underneath. So how does the example continue? We now go to the next node in our backtracking. These one we can ignore. We find a 14. Now this could be an interesting choice here, because now the interval for max to choose of is between 3 and 14. So we need to continue the search. So now this one has to be adapted. The beta value of this node has to be adapted. This means that the beta value of this one has also been adapted. So you always need to do the bookkeeping that you keep up with the values of alpha and beta. But you still have to go through the entire tree. Then this one becomes 2. We've calculated that one, but then we know that max will now choose 3. Yeah, because this would have been 2. This interval is not included in this interval above, and that means that max will choose this one. So we've now calculated exactly the same. We still have the value 3, but we've done so without calculating this. And this was now part of the one direction. This also works in the other direction. So if you have a beta value and you have the choice by min determined, so we have again these two sides of the algorithms that work exactly the same way. And this is a pseudocode for this algorithm, how this works. Again, you have a function that's called alpha-beta search on a state. You want to know what is the action I have to take. So you calculate the max value for this state based on the initialization of alpha value being minus infinity, beta value being plus infinity, and then you return the action that gives you the maximum value for the max player. And how is now the max value calculated? It is simply calculated. You have as input, you get the alpha beta, and you return the utility value. And what you basically do again is test whether you have a terminal, and in that case you give the utility or the heuristic value back. Otherwise, you look at all the successors. You take the first one, you take the maximum of the values underneath, you do the min tree evaluation again, and you take the alpha and the beta as your parameters. And then once you find something, you have to adapt the alpha beta value, and you return the new value for alpha as a maximum between the existing value and the one that you found in the tree underneath. And then you have exactly the same for the other direction, because of course max wants to maximize and min wants to minimize, so we need the alternating states. And again, you see here the min player adapts the beta value. And basically, this is the second task for the second assignment. If you manage to write the simple min-max, which I think most of you should be able to do, then the challenge is, can you also extend this towards an alpha-beta pruning? The method itself has very nice properties. And I think the most important one is that it's a complete method, as it's called. It doesn't change the results. So we still get exactly the same results with an algorithm applying minimax, without alpha-beta pruning, and with alpha-beta pruning. And why is that the case? Because we've shown that the crosses, the nodes that we could have expanded, would not have improved my results for max, because I know that I could not have found a better result. So there's no point in calculating them. But there is no information loss in alpha-beta pruning. And as I also said, it's not just that the end nodes, the leaves that we can prune, but it's the entire subtrees that could be underneath. So we can basically stop evaluating a subtree by just looking at one path until the node where we find this this alpha-beta conflict or so. And if you move if you order the moves effectively, then this can really help the pruning. And the theoretical result is, of course, this is not always working in practice, that if you have a perfect ordering for your alpha-beta pruning, then the time complexity can be reduced by this factor m divided by half, which in practice means that you can look twice as deep as without the alpha-beta pruning. Yeah. So that's an important result, because if we have our game, if we have to look through a complex game, whether you can look ahead 5 steps or whether you can look ahead 10 steps is a very, very big difference. And in our Schnapsen games, the complexity of the game is so small, I would say, that the difference is not that big. So even if you play these if you go systematically through all the 14,400 different states of the game, that is still sort of in milliseconds for your machine. But if you want to run an experiment in which you compare different techniques, then if you can be faster, that really makes a difference. If you are faster per game, and if it's only 30% faster, still your experiments will take 30% less. And particularly for games with a bigger search space in the perfect information part, you really need this kind of technology. Because for chess, looking ahead 3 or 6 moves really makes a big difference quality-wise. So these are the 2 classical algorithms that you need to know and that you need to understand, and that you also need to calculate on a piece of paper. And I would again recommend you to really do this on the basis of the pseudocode, so that you also understand how the pseudocode works, and then do the extension to your own code and have your intelligent agent calculate these min-max values and have them use alpha-beta pruning to be more efficient. And that starts, in my view, by really trying to be the algorithm yourself on a piece of paper. Start with calling the min-max value with the initial state of the example that I gave you, plus the minus infinity to plus infinity. Then go through all the lines of the codes. What would now happen if I was the computer executing the program? Because that gives you a good feeling how this algorithmic idea is. So now we have if we go back to the Schnapsen game, we have, of course, now dealt with the second phase where we have perfect information game, where we just need to apply min-max and we are done. We have to take sort of a small adaptation if you implement min-max. Remember that the order of the games is not altering systematically always between min and max, but that if you play a card and you win the trick, then you're allowed to continue. So it could be min, max, and if max wins, then max again, and then min. So it could be a bit more complicated in the way that the algorithm then has to be applied, but the principle is, of course, exactly the same. So that is the second part of the game, which I think we now have under control, we now understand. But of course, we have the big problem of the first phase. And here we have a really dramatic problem, because we now look at an imperfect information game. And even though, so this is the situation as it looks like, I know my 5 cards, and I know the trump card, and all the other 14 cards, I do not know where they are. And that might not look and sound so difficult, but it is. It is complicated. So before I show you how we are going to deal with this in Schnapsen, there is some theory about, or some ideas about search with partial information. This is not necessarily the game, the gaming scenario, but this also holds in more simple cases, even if you don't have an adversary player. And so basically, if you do not have perfect information, you need to be aware of what could happen. You need to understand the different situation. In many cases, the problem is that you do not have the sensors, the necessary sensors to give you the information. And you could, for example, only measure or when you're already in a certain situation. So we need to come up with an idea or a theory of how to deal with this imperfection. And the way I want to do that is to go back with a very simple example, and that is the example of the Hoover that cleans the rooms, remember. So now the task was start in any of those 8 situations with the 4 actions, going to the left, going to the right, hoovering, and why is there a 4th one? So now the problem is, if you do not know where you are and you do not know whether it's clean or not, if you have no information about the outside world, is there still anything that we could do in terms of writing an intelligent agent that cleans? So are we here depending on the perfect information about the rooming situation? And the idea here is what's called the beliefs states. The belief space is the set of all the possible states that you could be in. And if you are systematic, and if we have a good representation of the problem, then we can systematically enumerate all the possible states we're in. So let's look at the hoovering situation again. If you have 2 rooms and you don't know anything whether it's clean or not, then basically we have this situation. I don't know whether you can see this from the distance, but these are all the possible states that the Hoover could be in, or that we are in. Namely, the one where the Hoover is in two dirty rooms, it's on the left-hand side, on the right-hand side, so basically no information. So we have still all the 8 possible states we could be in. So now we can, based on this, all these possible states we're in, we could still do some action. So the action would be, for example, let's move to the left. Yeah. So this action. If I am in a room on the right, after this I will be in a room on the left. So all the states where the Hoover is on the right position will for sure not be valid anymore after I've taken the action. So basically, these are all the states where the Hoover is in the left-hand room. Yeah? So this is a belief state where I have no information and where the Hoover could be everywhere. And after one action, I move from one belief state to another one. So one interpretation of the world, so to speak. And the same, of course, holds for the right-hand side. So if I have a right action, then we're on the right. If I have a hoovering action, a sucking action, then what I know is that the room where I have been in is now clean. And then I can continue doing that for all the different belief states that I am in. So how would the belief state change if I would take a certain action? So after I've gone to the left-hand side and I clean, then I can only be in one of those 2 situations. Yeah? And then I can take an action. I can take the action, I go to the right, and then I could be in these 2 states. And then again, I have the action that I could go to the left again, I could suck again. And if I suck, if I clean the room, then I know that I'm in a gold state. Yeah? So basically, by maneuvering through the belief states, I can still find a valid course of action. So here I have this belief state. I go to the left with my Hoover. I clean the room. I go to the right, and I clean again. And then I know for sure that I found a valid strategy to clean the rooms. Yeah? So the idea here is that we're looking at sets of possible states and maneuver between the sets of possible states by some actions, and then we can do simple classical search as we did normally. So now how we apply these ideas to Schnapsen. The idea is basically, there's nothing happening here, that each of the possible card distributions of cards are belief states. So I would have a state in which the 14 cards that I'm not aware of yet are distributed in one way, and then I switch parts of the cards, I get another belief state, and basically you can now reduce the problem of dealing with uncertainty in this game to a classical game, search game, for these situations, if there wasn't the problem that the number of belief states is huge. So what I skipped here very briefly, if we have S states, then we have 2 to the power of S belief states, and that obviously creates an enormous problem again. So note that there is no element of chance in the game. So when we start the game, the whole situation, the whole game is deterministically determined. So the 9 cards in the pile, they are unknown, imperfect information, but they are fixed. So there's nobody reshuffling the cards in the middle. So I can do planning, I can do reasoning over all the possible beliefs I have. So if I have uncertainty, I also have imperfection, but not the other way around. So let's look at one way of thinking of the game of Schnapsen now, in terms of what does a state, for example, mean, and what does a state transition mean. If you look at the implementation of the game engine, so not your own part that you get to implement, to work on, but the game engine itself, then you will see that it has some kind of perfect information representation of the games. So that's what I mean, there's no element of chance, because the game engine knows where all the cards are. So it knows that it is in the hand of one of the players, of the max player, and this one is on the pile. So I think we have these would be in the pile after some situations. So basically, there is a representation for the whole game as a vector somewhere implemented in the game engine. And then what your agents get is this subset of it, where you know your hand, you know the cards that have already been played, that is known, but there's a lot of cards where we do not know where they come from. And now all this player information we could turn into belief states. As the minimax, as you can imagine, does not work, because on this on the imperfect elements we do not know what to do. And if we use belief states, then we have enormously many of them. So unfortunately, we cannot do the systematic search to sort of cut a long story short. This nice min-max algorithm that we have does not work for the first phase of Schnapsen. So we cannot do systematic search simply because there are too many belief states and the complexity of the problem is too high in this first phase, even though we are only talking 20 cards. So it's, I think, amazing how complex this very simple game is if you play it, and how many different games there would be given a certain card of hands to write a program that can play optimally. And that's why this is still a non-solved problem. So it is a simple game, but it's not a simple problem. And basically, the way we are approaching this in the other phases of the course, and the implementation that you have already gotten contains one bot which is called the RDeep player, and the RDeep thing does basically a random perfect information Monte Carlo sampling. This is what you also find in the literature. And basically the idea is that in the first phase of the game, you take a random sample out of the possible belief spaces, and then you play randomly the game on the basis of these belief spaces up to the phase 2, on which you can then, on the perfect information, play your Alpha-Beta Pruned minimax, and then you get a result back to your node, to your algorithm that you can average over, for example. So I think that is what the RDeep algorithm does. It goes, it does a random rollout, and it just averages over the number of times it wins, and the ones where it wins most, that gives you then the strategy for choosing the next move. So this is, as I said, this random game that you play is called a random goal, a rollout, which assumes perfect information. and then you average over and you select the maximum value. And that is actually very, very similar to what you do in AlphaGo, apart from the fact that they use some more clever way of looking through this whole search space. Because our search space with the belief states that we have to treat is comparably large to the search space of Go. They use this advanced data structure of Monte Carlo tree search, which helps you choose the right part of the tree. And in this course, we have the RDeep at the moment, which is a very, very simple random rollout and then sampling algorithm. So what have we seen? We've seen that there is a minimax and Alpha-Beta Pruning, which are very good algorithms and the standard algorithms if you play adversarial games with perfect information games. As soon as you move to the phase one, where you have the uncertainty about the imperfect information, you don't know what the adversary's cards are, you really have a problem. And then we have to move to some kind of sampling, and actually it's bloody difficult to beat this very simple, relatively simple algorithm. So next week we are moving from this search paradigm to modeling and dealing with uncertainty, and then we look into learning before we go back into more human kind of reasoning. And next week Michael will take over the lectures. So thank you.